So when this topic is usually taught in schools, it's usually called the laws of indices, and I really don't like that name because the word law kind of implies that it's a made-up rule. Like, a law is when somebody makes up a rule and everyone just has to follow it, just because that's how it is. But this is kind of the exact opposite of what's going on here, because these quote-unquote laws of indices aren't really laws. They all make sense, and you can really see that they all make sense. They weren't made up. So instead, they're kind of shortcuts. Instead of writing out instead of writing out the powers as multiplication and simplifying it like that, we can just use these shortcuts instead. So I'm going to show you today how all of these little quote-unquote laws relate to each other and give you a deeper understanding of what they actually mean. For example, why is a fractional power the same as a root? Or why is a negative power the reciprocal? And all of that. I'm going to show you how all of these kind of interlink with each other, and if we mess around with some rules, we get other rules popping out, and it's quite interesting. Now, in order to do that, I need you to forget everything you know about indices and all the rules, and I need you to have a piece of paper and a pen as well. And if you need to pause the video when I tell you to, because if you want to appreciate the beauty of maths, you have to understand maths. You have to kind of experiment by yourself, and if you don't experiment by yourself and you're just told everything, well, then you're not really discovering, and maths is all about discovering. So I would really urge you to pause the video when I say to, and other than that, let's go. So I guess first of all, it's quite important to think, why do we actually use indices? And was thinking of making another video about kind of the word exponent or index or power and kind of where the words come from and the history of exponents, but that's not what this video is about. But basically, old mathematicians were like, okay, well, when we're multiplying things together, I don't really want to write x, 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 and then if I have that multiplied by like x, 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 it's like, oh, it's going to be so long to write out. So they wanted a shorter way to do it. I'm going to skip over all the history. As I said, I'll do that in another video. But basically, they were like, right, let's write this number up in the top right, and that's what we're going to call an exponent, because exponent means kind of put forth. So we're kind of putting a number in front. We're putting a number forth in front of the, we're putting the power in front of the base. We're putting it forth. That's where the word exponent comes from. It comes from exponentem in Latin, which means put forth. So they were like, right, instead of saying this, we're going to write, so this is 1, 2, 3, 4, 5, 6, 7 x's multiplied by each other. That's x to the power of 7, and that's multiplied by x to the power of 4. Now, if they wanted to simplify it in the old way they did it, they'd write, okay, well, we have 7 of them. We have x, 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 x. Okay, wait. So 1, 2, 3, 4, 5, 6, 7. And then we have these 4 as well when we're multiplying x, 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 x. So by that logic, when we multiply these two together, what should the answer be? How many x's do we have here? Pause the video if you didn't. But basically, the reason, or what it's going to be x to the power of 11, because we had 7 x's here, we had 4 x's here, when we multiply them all together, that's 11. I know this is quite basic, but just bear with me. So we clearly, when we're multiplying numbers with powers, and they have the same base, we add the powers. Now, I want to ask you, why can we only do it when they have the same base? Or another example, again, something that I see people mess up a lot, is, for example, if they have like 2 squared times 2 cubed, I see them sometimes write out as 4 to the power of 5. They're like, well, 2 times 2 is 4, and then add the powers, you get 5. Why is that wrong? And then as well as that, I want you to think about, why can't we do a rule when we have different bases, like 3? Or I guess if you want to think of a numerical example, which might be easier to think of, why can't we do 2 squared times 3 squared? Why can't we simplify that? Or I won't say 3 squared, that's a bad example. 3 cubed. Why can't we simplify that? I want you to pause the video, mess around with both of these examples, and see if you can understand why this one is wrong and why we can't do anything to simplify this. Well, the reason that this isn't the case is because, as I said, if you write it out the long way, like up here, we'll have 2 times 2 multiplied by 2 times 2 times 2. How many 2's do we have in total now? We have 2 times 2 times 2 times 2 times 2. That's 5 2's. That's 2 to the power of 5. You can see there's no 4's here. It's only how many 2's we have, so we don't multiply the bases. And then here, why can't we simplify anything? Because we have 2 times 2 times 3 times 3 times 3. There's nothing, like if we get rid of the brackets, as we did up there, if we have 2 times 2 times 3 times 3 times 3, there's nothing we can really simplify there. There's still 2 2's and 3 3's, so there's nothing we can do there. That's why the rule only works when you have the same base. So when we multiply, that implies that we add the powers. Now, if dividing is the opposite of multiplying, what would you expect to happen to the powers then? If dividing is the opposite of multiplying, what's the opposite of adding? It's subtracting. We subtract the powers. That's what our intuition should say. Now we need to see if it's actually true. So let's see if we have 2 to the power of 5 over 2 squared, for example. Well, that's 2 times 2 times 2 times 2 over, sorry, one more, times 2 over 2 times 2. And what happens here? Well, technically, we have 2 times 2 times 2 times 2 times 2 times 2 divided by 2 divided by 2. They kind of undo each other. So if we multiply by 2 and divide by 2, they undo each other. It has no effect because 2 divided by 2 is just 1. Same thing here. What are we left with? We're left with 3 2's, 2 to the power of 3. You can see however many there are at the bottom, that's going to get rid of that many on the top. Therefore, as we expected, if we have, I guess, a to the power of a number, or what, how did I write it up there? I didn't actually write the rule. If you have a to the power of a number over a to the power of another number, it's going to be a to the power and minus the powers as we expected over here. Now I want to see if we can get an interesting other rule from this. So the idea that I'm going to put forth to you is we're going to combine this rule with the other rule, and the other rule is going to be a to the power of x times a to the power of y equals to a to the power of x plus y. Okay, we're going to combine these rules. I want to see something interesting that happens. So I want you to see, using this rule, can we somehow change this? In particular, can we change this to be something else? Pause the video, give it a go. Well, if you didn't figure it out, what we can do is, so obviously we can't really do anything with the left-hand side. With the right-hand side, though, according to this rule here, we can split these up as multiplication, can't we? So here, we can split that up into multiplication. That's going to be a to the power of x times a to the power of minus y. Why? Because when we multiply these together, we add the powers, we get x minus y, as we have here. Now, what do you think we could do here to both sides that would kind of give us an interesting something to think about? Pause the video, have a think, mess around with it. What could we do here? Well, we notice we're multiplying by a to the power of x on both sides. If we divide both sides by a to the power of x, so if I just move this over a bit, if we divide by a to the power of x and over a to the power of x, they'll cancel. What we have is 1 over a to the power of y equals a to the power of minus y. This is really interesting. So at the start of the video, we didn't really understand what the hell is meant by a negative exponent. Well, here we can just figure it out by using those two rules. See that a negative exponent is the same as 1 over that exponent, which is quite interesting. Now, there's actually other ways to show that this rule is the case. For example, you can actually do it without having to do anything like that. So let's say we have, the way that you can think of this is, let's say we have a cubed over a to the power of 5 or something, for example. Okay, well, there's two ways we can think about this, kind of like we did up here. That's a to the power of 3 minus 5, which is a to the power minus 2. Now, there's another way we can think about it, which is if we expand it out, we'll have a times a times a over a times a times a times a times a. What can we do here to simplify it? Well, we obviously, dividing and multiplying our opposites, what we get is 1 over a times a, which is a squared. So that means that these two things are the same, which, as you can see, agrees with the rule that we derived up here. Okay, so now we understand what's meant by a positive power. Obviously, we always knew that. Now we understand what's meant by a negative power. The only other type of powers are fractional and 0. Now we're going to start off with 0. What the hell happens with the power of 0? Well, how can we use either of these rules to figure that out, maybe? Well, if we use this subtraction rule, we could get something minus the same thing, and that'll give us 0. So let's give that a go. So the two numbers I'll choose is, let's say we have a to the power of x over a to the power of x. That's going to be a to the power of x minus x, which is equal to a to the power of 0. Now what happens in this fraction here? Well, if you have something divided by that same thing, that's just going to be equal to 1. That means that 1 is equal to a to the power of 0. So this is a very interesting fact. No matter what you have, if you have something, any number to the power of 0, it's equal to 1. Now, there's obviously a little argument about 0 to the power of 0, which I might make another video about. This is special because technically, one rule that you might know is that 0 to the power of anything is 0, but then we just said that anything to the power of 0 is 1. So that means 0 to the power of 0 is equal to 0, but also 1. So there's actually a few different arguments for that, and it's quite interesting. I'll make another video on that. That's not really to do with today. This is just for the rules. So already we have talked about this rule, this rule, and these two. So already we're kind of getting somewhere. Let's talk about this one next. So, and this is one that I used to always get really confused about. I'm sorry, it wasn't this one, but it was unrelated to this one. I'll get to the one that I always got confused about in a second. So we have, for example, a to the power of, or I guess we'll say 2 squared, the whole thing cubed. Now, it's something that might not be obvious is, well, what the hell do we do with that? Again, we're going to do the same that we've been doing before. We're going to break it down into the most basic way we can think about it. That's going to be 2 times 2 times 2 times 2 times 2 times 2, 3 times. How many 2's do we have? Well, we have 3 sets of 2 2's, so that's 6 2's in total. That's 2 to the power of 6. That's the reason why we multiply these. And because we know that we multiply those, that means it's also commutative, this operation. So first of all, we can say that a to the power of x, the whole thing to the power of y, that's equal to a to the power of xy. And because multiplication is commutative, that means that's also equal to a to the power of y to the power of x. As we'd see here, if we had instead 2 to the cubed squared, it's the same thing, because then we'd have a group of 3 2's multiplied by a group of 3 2's. How many 2's do we have in total? 6 still. So it's all the same. This doesn't seem too, I guess, mind-boggling now, but you'll see why it is later. So sorry, that was a little bit of an aside. We've dealt with the power of 0, we have positive powers, we have negative powers. What about fractional powers? So that's going to be quite interesting. Like, for example, what does 2 to the power of a half mean? I guess a half is the simplest fraction we can think of. Well, let's think of it this way. We know that 2 to the power of a half multiplied by 2 to the power of a half, that should be equal to 2 to the power of 1, because we have to add the powers. We know that that has to be true. So what's it called if we multiply two numbers together and it gives you that number? So 2 to the power of a half times 2 to the power of half, that just gives us 2. There's another kind of thing we know in maths that has this property that if you multiply it together, it gives you that number. What is it? It's the square root, because if we have the square root of 2 times the square root of 2, that's the same as the square root of 2 squared, which is, they all cancel out, of course, and we get 2. That means that 2 to the power of half is equal to the square root of 2. Now, this might not be a very, I guess, concrete proof for you, so let me do it a bit more kind of concretely, I suppose. Let's say we're trying to figure out, we now have a sneaking suspicion, so this obviously isn't too formal. Let's say now we have a sneaking suspicion that the power of a half might be the square root. How could we prove that properly? Well, let's say x to the power of a equals the square root of x. So we know that x to some power will give us the square root. We're going to assume that these are the same things. Well, how do we work with this? Well, we could square both sides to get rid of the square root. So we'll get x to the power of a, the whole thing squared, equals to x. Now we know what to do with powers, don't we? When a power to a power, we can multiply them. It's x to the power of 2a equals x, technically to the power of 1. Now, since they have the same base, that means the exponents must be the same. That means that 2a equals 1. That means that a is equal to a half. Wow, okay, we just proved that the power of a half is definitely the same as the square root. Now, for you, I want to see if you can prove or figure out what power, x to the power of what, will be equal to the cube root of x. I want you to give that a go by yourself. Now, if you did it properly, you'll cube both sides. You'll get x to the power of 3b equals to x, and then the powers are equal. You'll get b as a third. So that means that the cube root of x is actually just the same as the power of 3, or a third, sorry. That means, in general, the nth root of x is the same as x to the power of 1 over n. That's very interesting. But that's only 1 over a number. What about if we have, like, 4 over a number? Well, all we have to do is just do both sides to the power of 4, because... Or I won't say to the power of 4, I'll just do a random power. Let's say if we do it to the power of n, we'll do m next. Okay? Then we get the nth root of x, all to the power of m, is equal to x to the power of, and then we multiply the powers, remember, m over n. So you can see that if we have a fractional power, the numerator will be the power and the denominator will be the root. Very interesting. There's actually one more thing we can do with this, and that's to do with the rearranging. Do you think it matters if we have the nth root of x to the power of m? Do you think that's the same as doing this? X to the power of m. Do you think it's the same, and why or why not? I want you to kind of mess around with it. Why not should that be the same? Well, it should be the same, and why is that? Because the square root is a power, and this is a power, and we said that when we're multiplying powers, it's commutative. So why should these be the same? Because we can write the nth root of x to the power of m as x to the power of m to the power of 1 over n, can't we? And then we can rewrite that. We can remember, because it's commutative, we can swap them around. X to the power of 1 over n to the power of m, that's the exact same thing. That means that's the same as the nth root of x all to the power of m. So as you can see, it all makes sense. These are the same the other way around, and this is how we can interpret fractional powers. So now we've done most of the rules here, I just want to talk about these two as well quickly, because this is the one that really confused me when I was learning. So I very distinctly remember, I'm pretty sure it was something like 2x squared. okay? And I remember asking my teacher, well, if I'm squaring it, am I squaring just the x, or do I square both of them? And she said, you just square both of them. And I was like, okay. And I always kept forgetting that, and I kept doing it wrong. But if I could understand why, then I could have gotten it. I could have remembered it so much more easily. So I want you to think, if you didn't know how to approach this, how could you approach it? So what could you do? Well, if you're stuck, well, remember, up here, the way we figured out all of these rules is by thinking of exponentiation as kind of a more simple thing, as multiplying. So do the same here and give it a go. Well, if we think of this as multiplying, that's the same as 2x times 2x. And multiplication is commutative and associative, so the ordering and the grouping doesn't matter. So that kind of means the same thing, whatever. So we can actually write this as 2 times 2. I actually won't use an x because it's going to confuse us with the x. 2 times 2 times x, which is going to be equal to 4x squared. So as you can see, if we have a product, we multiply both of them by the exponent, okay? So in general, if we have ab to the power of x, that's equal to a to the x, b to the x. And that's the rule, that's just what my teacher told me. If I understood this, I'd be able to remember it way easier. Now, using that same argument, what do you think a fraction a over b to the power of x should be? Well, there's a few ways of going about it, but remember that taking, I guess, dividing is the same as a negative power. So you can see, if we can think of this as a b to the minus 1 to the power of x. And now we have multiplication, and we know when we're multiplying that this rule is true. That means that this is going to be equal to a to the power of x, b to the power of minus x, which is the same as a to the x over b to the x. So we see that it is true, or we can do it another way. We can think of it as the same way that I did up here. If we have a over b, we'll just say squared for now. That's the same as a over b times a over b. Now, obviously, with fractions, we multiply the tops and the bottoms. I will explain that in another video. I think it's quite interesting because people take it for granted. We get a squared over b squared, and they're the same. You can see we just gave the power to each part. And that's the reason why all of these quote-unquote laws, they're really just shortcuts. Instead of doing it the long way like I've done here, they're just quicker ways of doing it so that you don't have to keep doing this every time. And they're not things that should be memorized. They should kind of make sense, and you shouldn't have to memorize them. You should just be able to understand them, and then you can just use them all the time. So I hope that was really interesting. I'm probably going to make a video about the kind of history of indices, and I'll probably make one about logarithms as well, because I think they're even worse taught than indices. And yeah, I hope you enjoyed. Please comment ideas if you want. If you enjoyed it, or any critics, anything, a comment would be greatly appreciated. Thank you.